Hey everyone, and welcome to The Explainer. Today, we are getting into the bedrock of mathematics. We're talking about the absolute fundamental rules that make our entire number system work. We're going to build it all from the ground up.
And I want to give a huge special welcome to all the BSED math majors from Romblon State University, San Fernando campus. And of course, a big shout out to your professor, Dr. Vilran M. Vibas. It is truly awesome to have you all here. You are the future, the next generation of math educators, and we are so excited to go on this journey with you.
You know, this quote from the great B.B. King really hits the nail on the head for what you're doing right now. The things we're about to explore, they aren't just for a test. This knowledge becomes a part of you, a tool that you will have forever. And believe me, that's going to be your superpower in the classroom. All right, so here's our blueprint for today. First, we'll talk about the rules of the game, why we even need these things called axioms. Then, we'll build our two main pillars, addition and multiplication. After that, we'll lock them together with a keystone piece. And finally, we'll step back and admire the solid foundation we've just constructed together. Okay, first things first, the rules of the game. Look, you can't play any game, I don't care if it's basketball or chess or math, if you don't know the rules. Axioms, they're just that. They are the absolute, non-negotiable, fundamental rules of mathematics.
Think about it this way. If math is its own language, then axioms are its grammar. They're the rules we all have to agree on so we can communicate clearly and build things that make sense. Without them, we'd all just be speaking mathematical gibberish.
So what is an axiom, really? Well, it's just a statement that we all agree is true without needing to prove it. It's self-evident. It's the starting point, the solid ground that we can all stand on so that we can start building all the other amazing, complex ideas in mathematics.
And listen, for you, as future math teachers, this is everything. It's one thing to know that 2 plus 3 equals 5. Any student can memorize that. But your job, your real superpower, is to explain why. Why does it work that way? Understanding these axioms gives you the why. It's the difference between just being a human calculator and being a true educator.
All right, let's get to work. It's time to pour the concrete for our very first pillar. We're about to lay down the 5 fundamental truths that control every single thing we do with addition in the real number system. Here they are, the 5 big rules for addition: closure, commutative, associative, identity, and inverse. Let's break these down one by one and see how they create this perfect, self-contained system. First up is the closure axiom. This one's actually pretty simple. It just means that if you take any two real numbers and you add them together, your answer is guaranteed to also be a real number. You can't add 2 and pi and somehow get an answer that's, I don't know, the color blue. You always stay inside the set of real numbers. The gate is closed. Next, we've got the commutative axiom. And I guarantee you use this every single day without even thinking about it. It just says that the order you add numbers in doesn't matter. It's kind of like your commute to work. The distance from home to the office is the same as the distance from the office back home. A plus B is always going to give you the same result as B plus A. And this slide just lays it out perfectly, right? Formally, we write it as A plus B equals B plus A. But in the real world, it just means 5 plus 3 is exactly the same as 3 plus 5. Both roads lead to 8. This axiom is the guarantee that this works for every single real number. Now don't get this one mixed up with the last one. Our third axiom, the associative axiom, is all about grouping, not order. It says that if you're adding a long string of numbers, it doesn't matter which pair of numbers you decide to associate with and add together first. The final sum will be the same no matter what. All right, the identity axiom. This one introduces a very special number into the mix, 0. 0 is called the additive identity because when you add it to any number, that number gets to keep its original identity. 7 plus 0 is still 7. It doesn't change. It's like the neutral player on the team. And that leads us perfectly right into the inverse axiom. This rule promises us that for every single number A, there's a matching opposite, which we call negative A, that gets you right back to our identity element 0. So the inverse of 5 is negative 5, because 5 plus negative 5 gets you back to 0.
every number has a partner that cancels it out.
Fantastic. Our first pillar is up and solid. So now, let's build the second one, the axioms of multiplication. And what you're about to see is just beautiful. It shows you how elegant and logical math really is, because these rules are an almost perfect mirror of the ones for addition.
Look familiar? Yeah, it should. We've got the same 5 big ideas: closure, commutative, associative, identity, and inverse. This isn't a coincidence. It shows you just how deep the logical structure of our number system really is. Let's see how they work for multiplication.
So let's just do a quick side-by-side. Closure for multiplication? Yep. You multiply 2 real numbers, you get a real number. You stay in the club. Commutative, of course. 2 times 8 is the same thing as 8 times 2. The order doesn't matter. The logic is exactly the same. And just like with addition, the associative axiom for multiplication is all about grouping. If you're multiplying 2 times 3 times 4, you can do the 2 times 3 part first, or you can do the 3 times 4 part first. Doesn't matter. Either way, you're going to end up with 24. Okay, now here's where things get a little different. A key change. For addition, our identity, our neutral number, was 0. For multiplication, think about it. What number can you multiply by that doesn't change the original number? It's 1, right? 17 times 1 is still 17. So, for multiplication, 1 is our identity element. So, if 1 is our new identity, then the inverse axiom has to tell us how to get back to 1. For any number a, its multiplicative inverse is its reciprocal, 1 over a. So the inverse of 5 is 1/5 because 5 times 1/5 gets us back to 1. But, and this is a huge but, there's one number that's the exception to the rule: 0. You can't divide by 0, so 0 does not have a multiplicative inverse. That's a critical detail. Okay, we've got our 2 pillars standing tall. We have the rules for addition and we have the rules for multiplication. But right now, they're just 2 separate towers. We need the final piece, the keystone that locks them both together and makes the whole building strong. And that piece is the distributive axiom. And here it is. This is the one rule that brings both operations, addition and multiplication, into the same equation. It tells us that multiplying a number by a group of numbers that are being added is the same as distributing that multiplication to each number inside and then adding the results. Honestly, this is the rule that makes most of algebra possible. It's how we expand and simplify everything.
So let's just pause for a second and look at what we've actually done here. By simply agreeing on these few fundamental truths, we've managed to construct this incredibly powerful, stable, and logical system from scratch.
These 11 rules we've covered, the 5 for addition, the 5 for multiplication, and the one distributive rule that ties them together, they have a formal name. Altogether, they're known as the field axioms. And any system that follows these 11 rules is called a field. You've just built the definition of one of the most important structures in all of mathematics.
But we're not done yet. Our building is strong, but it's missing something. We know how to add and multiply, but we have no official rules yet for saying one number is bigger than or less than another. That's what's coming in part 2 of this explainer. We're going to build right on top of this foundation with the axioms of order.
So I'm going to leave you with a little puzzle to think about. Now that you have these 11 official rules, how could you use only those rules to prove something we all think is super obvious, like the fact that any number multiplied by 0 equals 0? That's the next step in your thinking. Not just knowing the rules, but using them to build new truths.
To all of you at Ramblon State University, I really hope this helped you see the deep beauty and logic behind the math you'll be teaching one day. If you enjoyed this and want to keep learning, please go subscribe to the No Problem Only Solution YouTube channel. Give this explainer a like and maybe leave a comment. Keep asking why, stay curious, and never stop building. We'll see you all in part 2.